Hi everyone. So in this video I'm going to go over how to solve a rational equation. First, just to define what a rational equation is. Rational equation is an equation with one or more rational terms in it. And a rational term or a rational function is just a function of two polynomials. So sometimes it's easier to see what I'm talking about rather than to look at the definition. I'm talking about seeing a polynomial for the numerator and a polynomial for a denominator. It's kind of like a fraction of polynomials. As far as the steps I'm going to be showing you for how to solve one of these rational expressions algebraically, we're going to start off by factoring the denominators and then find the least common denominator out of them. So we can find the least common denominator by multiplying all of our denominators together, not needing to repeat any terms that were already used in one place or another. Next, we're going to multiply everything in the entire equation by that least common denominator to clear out the denominators of my fraction. Next, we will do any distributing or simplifying that we have. Finally, we will solve for the variable. Usually it's going to be an x that they will give you in the equation. And then step 5, we're going to be checking for something called an extraneous solution. And we'll do that by plugging the solutions we got back into the original equation. I'll show you more information on that here on the next slide. So an extraneous solution, I often kind of casually refer to these as fake answers. So you might go through the entire solving process and get a couple answers at the end, like x equals 2 and x equals 5. Well, once you finish solving, we're going to plug the x equals 2 and x equals 5 into the original equation, and we're going to see if any of them should not be included in our list of final solutions, because by plugging them in, we may find that one of our fractions that we're working with ends up being undefined using that given number. So if I find that the answers are x equals 2 and x equals 5, and then I plug them into the original equation, and I found that x equals 2 makes one of the fractions a denominator 0, then I would eliminate that answer from my list of solutions. That would be an extraneous solution, hence why I sometimes kind of casually refer to them as a fake answer. But let's look at some examples, and then maybe this will make more sense for you. So here is my equation. I have the three parts, 1 over x, 1 over 5, and 3 over 2x. I'm actually going to rewrite these because I like to have a little bit of space between my numbers. So I have 1 over x, 1 over 5, and 3 over 2x. Now, the first thing I mentioned was that we need to do any factoring in the denominators, but these fractions are all so simple that there's really not any factoring to do in this case. So I can kind of skip that first step for my first example. Next is we find the LCD, which stands for least common denominator, and I can find that by taking each of my denominators and multiplying them together. So my first denominator has an x in it. My next denominator has a 5. That's something new. I didn't already have that in my LCD, so I'm going to incorporate that into the LCD. My next denominator has two pieces, a 2 and an x being multiplied together. Now the x I already have taken care of. Since it's not like x to a different power, I can just use the x I already incorporated into this and not repeat the x. However, the 2 has not been multiplied in yet. So I'm going to include that into my LCD. And then if I multiply all these numbers together, in this case, I'm getting an LCD of 10x. So going back to my steps that I showed earlier, I have now found the LCD. Now I'm going to multiply each term by the LCD to clear out my denominators. So everything needs to be multiplied by my 10x. Now remember, when we say multiply by 10x, technically that means 10x over 1, not 10x over 10x, which is a common mistake. So I'm multiplying by 10x. If you want to write the over 1 part, just to make sure you don't make a mistake on your fraction work, there's nothing wrong with doing that. Now for the actual multiplications, what happens when I multiply these together is I have 10x times 1, which is just 10x, over 1 times x, which is x. I'm going to be able to reduce that in a moment, but for now I'm just going to leave it there. On the next fraction, I have 10x times 1 on top, over 5 times 1. And on the last fraction, I have 3 times 10x over 2x times 1. Now, all of these can be reduced. That's usually what you should expect to happen here. For example, the 10x over x, the x's would cancel. So that's just going to be a 10. Here I have 10x over 5. Well, the 10 over 5 reduces. That's the same as just saying 2, 10 divided by 5. And then on the last one, I have the x's will cancel. So the only other part I have to worry about is 30 divided by 2 is 15. So this has created a smaller and easier to work with equation. I no longer have a fraction to deal with at all. So now I can just go into my opposite operation steps. I'm going to subtract 15 from both sides and then divide both sides by 2. So I have found a solution. It's -5/2. And you could think of that in decimal form if you like. So I have a solution, but I haven't determined whether it's extraneous or not yet. So the next step would be to imagine what happens when I plug that -2.5 into my original fractions. All I'm really looking for is to see if any of them will end up being a denominator of 0. And in this case, -2.5 by itself is not 0. There isn't even anything to plug into on this fraction, so that one's fine. And over here, -2.5 times 2 would be -5, so that didn't equal 0 either. So that is my answer. We have my solution to the rational equations. Now let's look at a slightly harder one that will have an extraneous solution. My first step was that we might need to do some factoring. So on top, I don't have anything to factor for this first expression, but on the denominator, this is a trinomial, and the two numbers that multiply to 2 and add up to 3, that would be +2 and +1. So 2 times 1 is 2, 2 plus 1 is 3. That's my factoring for that trinomial. Again, I'm going to leave a little bit of blank space because I know I'm going to be multiplying some other numbers in here. So leaving some room, I'm going to have the next fraction, next rational expression. This one doesn't have anything to factor, so I can leave it alone. You can't always factor all of them. And then again, I'm going to leave some blank spaces, and I'm going to write my x minus 1 over x plus 1. Again, I don't see anything that I can factor there. It's not a difference of squares. There's not a GCF, nothing like that. So for finding my LCD, as I go through them, it doesn't really matter what order you go in. I usually tend to start from the left and go to the right. I see a factor with a denominator of x plus 2, so that's going to go into my LCD. That same fraction also had a denominator of x plus 1 being multiplied. That is a different number. Because remember, you can imagine a number being plugged in for x like 5. That means 7, and that means 6. So these are different numbers up here. Now the x plus 2, as I come to the next fraction, I've already got that in my least common denominator. That factor's already been covered, so I don't need to multiply it again. Same thing with the x plus 1. I've already taken care of that, so I don't need to add that in either. So I now have the least common denominator, which means my next step is to multiply everything by the LCD, x plus 2 times x plus 1. Doesn't hurt to write the over 1, like I said, so I'll do it again just for clarity. Now, something that can help you with simplifying, especially when you're dealing with factors like this when we're multiplying together, remember that you can cross-cancel from your multiplication here. If I multiplied these out and reduced, it would be the same as recognizing that, oh, there's going to be an x plus 2 on my numerator and an x plus 2 in the denominator. Well, since those fractions are being multiplied, they're just going to cancel each other out. So I can save time by doing that as I do the multiplication. I also have an x plus 1 in the numerator and an x plus 1 in the denominator, so those will cancel out. So all that's going to be left from these two fractions being multiplied is the x minus 1 over 1, which is just x minus 1. Great, so that fraction is done. For the next one over here, I see an x plus 2 in the denominator. I'm going to cancel that with the x plus 2 factor from the other fraction that I'm multiplying in. So now I only have to worry about 2x times the x plus 1. You may even want to go ahead and distribute that at the same time. So in this case, 2x times x is 2x squared, and 2x times 1 is 2x. For my last fraction down here, very similar process. I have an x plus 1 in the denominator. I have an x plus 1 in the numerator, so I can cancel those out. And then if you want to save yourself some room on your paper, try to do the distributing right now at the same time. So foiling is how a lot of people learn this. The x times x is x squared. I know that the outside and inside distributions are going to create positive 2x and negative 1x. So that'll be positive x. And then the last product is going to give me a negative 2. So if you want to do that as two steps, you absolutely can, but it does save room in your paper if you do the distributing at the same time. Next, I want to move all the terms to the same side of the equation. It doesn't really matter which way I move them, but I have more numbers on this side, so I think I'm going to move from the right side to the left side, but I could have done that the other way around. So I'm going to subtract the x squared over, and 2x squared minus 1x squared is going to be 1x squared. On the left side, I had a positive x and a positive 2x. That's 3x. But I'm also going to subtract this one over. So 3x minus x is 2x. And then I have a negative 1 and a negative 2 on the other side, so I'm going to have to add that 2 over. So negative 1 plus 2 will give me a plus 1. So at this point, This is broken down enough that I think we can just factor this. The alternative would be you might need to use something like the quadratic formula to find the other answers. But if I wanted to find numbers that multiply to 1 and add up to 2, so here's my trinomial factoring setup again. The two numbers would be 1 and 1, because 1 times 1 equals 1, and 1 plus 1 equals 2. So I actually have the same factor twice, so a lot of times we end up just writing that as x plus 1 squared. Well, as far as finding the individual answers from this, since you can normally set each factor equal to 0 as its own equation to solve it, in this case, it doesn't matter which one I pick. When I set it equal to 0 and solve, I just get x equals -1 for an answer. Let me write this over here. Okay, so x equals -1. However, I do need to go through all of my original fractions and see if any of them would end up having a denominator of 0. If a single one ends up being a fraction over 0, then I have an extraneous solution on my hands. So it would actually happen for this one too. It wouldn't affect this one. If I plugged in x equals -1, I'd have -1 plus 2 is +1. So this fraction was fine. But when I look at this fraction, plugging in -1 and then adding 1 would give me a denominator of 0. So that's the fraction that's going to make me call this one an extraneous solution. So if the question said find all the solutions, the problem is the only one I had I'm crossing out. It's extraneous. So I instead end up saying that I have no solution in this case. If I had two answers and one got crossed out and one didn't, then I would just list the one that hadn't gotten crossed out. But in this case, all of my answers got crossed out, so I don't have any left. So my final answer is technically no solution. Now let's look at a slightly easier part of dealing with solving rational equations. Let's look at the graphing approach. So the solutions will be x-intercepts that you can see on the graph. Basically just look at where the line touches the x-axis. If you see it touching at x equals 2, then that means x equals 2 is a solution. Sometimes they're going to ask you about a number where you do not see an x-intercept. So if you don't see the line touching the x-axis at a given value, then that means that must be an extraneous solution. It is not one of our actual answers. For example, you will have questions, or you might encounter questions like this where they say, hey, here are some possible solutions for this given rational equation. They might have given you the graph, or you might have to find the graph yourself by using like a graphing calculator, or maybe by drawing it by hand yourself. However, the main thing to focus on here is once you have the graph, what can I compare from the given numbers to the graph? At x equals 1, I do see an x-intercept. So that means that this is a solution. At x equals 3, I do not see anything happening here. So at x equals 3, there is a problem there. That one must not be a real solution. I would call that one an extraneous solution. And then the last one they gave me was x equals 6. At x equals 6, I do see another intercept. So that one is a solution. So if they ask you which ones are extraneous, I would just say the x equals 3. If they ask me which ones are my solutions, then I would say the x equals 1 and the x equals 6 instead. So it would depend on how the question is phrased. But that's it for the lesson on how to deal with solving rational equations, either algebraically or graphically.